All right, so example number 2, we're going to do a pure shear example. Right? So what do I mean by that? Well, what I mean is that there is no normal stress in the in the XY orientation, right? So this is our standard sort of horizontal slash vertical orientation, right? And there is no normal stress there. So the only thing that this stress cube feels right now is pure shear in this orientation. Again, in this orientation. Right? So let me draw the Mohr circle. We'll see how that looks. So this guy will do positive downward again. Maybe like that. Okay. So this is our sigma and this is our tau, right? It's not sigma xx, right? It's just sigma because, xx is only in the xy orientation, and this Mohr circle is going to be for all orientations. So this is just normal stress and shear stress. Okay, so first step is we're going to plot our point 1, which in this case is this 20 ksi, and 0. So that point 1 is going to be right here, right? So this guy is 0, comma 20, right? And then the next thing we're going to do is we're going to plot this guy up here, which is going to be 0, comma minus 20. Again, that is sigma yy minus 20. Right? So this vertical line, now the current stress state here, right, is a vertical line. Right? That's what happens when it's pure shear, right? It should make sense because I can't have any stress, I can't have any non-zero coordinates on the sigma axis, right? Because there's no normal stress in this orientation. All right, so then let me draw more circle, right? So I'm just gonna spin this guy around. Oh, geez. Spin this guy around. Hopefully I can do it. It's always a sort of a bit of a crapshoot if you can get it to, sort of register the way you want it to, right? So that's our circle. That one looks actually pretty good, right? So now our state of principal stress is here. Again, it's always there, right? Because it's always it always corresponds to the sigma axis, right? So in this case, this guy is sigma 1, and this guy here is sigma 2, right? Now, some of this is pretty straightforward, right? What is R, right? So R, you don't even have to compute it, right? It just equals 20 ksi, right? Because you can see the circle is centered at the 0, 0 point, right? And it touches minus 20 and 20, so the diameter is 40, the radius is 20, right? Pretty straightforward. The other thing that we can see here is that sigma 1, right, should equal 20 ksi, and sigma 2 should equal minus 20 ksi. Right? And again, it's just the radius. So the center is at 0, 0, right? So this guy is at 0, 0, and therefore the center plus an r and the center minus an r, that gives me my sigma 1 and sigma 2, right? And then my 2 theta p, right, is this guy here, right? And that's going to give me a theta p of 45 degrees, right? Why? Because it's 2 theta p on the circle that, so that's 90 degrees, and then on the cube, it's going to give me a half of that, right? So now I can draw my cube here. So let's see how I want to do this. I guess I'll try it like this. All right, close enough, right? So this guy here, right, that is 45 degrees, right? That, by the way, is exactly the same. I'm not going to do this every time, but I'll do it one more time here, as that angle, right? Both are 45 degrees, okay? So I started here, right? This was the X face. And if I rotate that X face counterclockwise, 45 degrees, right, I get the face that's, you know, heading to the upper right. So this guy here is my sigma 1, right? So this is sigma 1, and that is equal to 20 KSI, right? And then perpendicular to that, 180 degrees on the circle, 90 degrees on the cube, this guy is my sigma 2, and that equals minus 20 KSI. So that's interesting. I hope that you see that I can apply pure shear to a piece of material, right? And what comes out is, in that orientation, of course, pure shear, but 45 degrees from that orientation, I have pure tension and compression, right, that are balanced, right? So if you start with pure shear, the normal stresses are going to equal the same as the shear stress, right? And hopefully you can start to see that. I know I had mentioned this a few times before, but these shear stresses are trying to deform that cube like that. So what are they doing? Well, they're applying a compression force here and a tension force here, right? That looks just like what I drew in the lower right, you know? And you can see that just by the arrows and the way they're trying to deform it, right? So shear, pure shear, does result in tension and compression, just in a different orientation.